Hi, my name is Jesse Chick. I'm a vulnerability researcher with Trellix ARC, and in this video series I'll be walking you through my adventures with the Linksys WRT54GL, or at least the highlights of them. So this router first hit the shelves in 2005 and was supported through 2016, and according to some sources it's the best-selling router of all time. I have no idea whether or not that's still true, but needless to say it found its way into a lot of homes and businesses. So I found this router while I was rummaging around in the electronic waste section of our office building here in Hillsboro, Oregon, and wound up taking it back to the lab, getting it set up, and just having a poke around to see if I could find any vulnerabilities. As it turns out, I was able to find several ways to completely take over the device over the network, and we disclosed those vulnerabilities to Linksys last summer. Now, for various reasons, this research and its findings is not the kind of thing that we would wind up submitting to one of the big conferences. But I do feel that the process of finding the vulnerabilities really showcases a lot of the key methodologies that we on the Vuln research team use to hack devices of all kinds, while also being rudimentary enough to be accessible to somebody without a strong background in security or understanding of reverse engineering. So with that audience in mind, I really make an effort to explain key terminology, justify each step that I take, and describe which tools are valuable for which step, and that kind of thing. So if you're interested in learning how we go from a router in a box to having complete control over that device, or if you're looking to do some Vuln research of your own and are looking for some cues as to how to get started, I really think that you'll find this series valuable. So without further ado, let's get started. So to start things off here, I was able to find a ton of publicly available technical information about this router before I even bothered to set it up. So I'll just go through here and pick out the two avenues that I found to be the most valuable. So the first one actually came from the vendor's website. So we'll just go to Linksys, that's our vendor, and I'll just punch in the model number here. And the second result down is the product support page. So this has links to a user guide, which I didn't even bother looking at, but I did spend a lot of time with the firmware. So this router gets firmware updates just by you downloading it off of their webpage and then uploading it through the management console. There's no over-the-air firmware updates, so this is how you do it. And so you can download the firmware. I'm just going to download it directly into my Kali WSL install over here. And I'm also going to grab the release notes. We'll take a peek at those too later. So the firmware says EMEA only. I'm pretty sure that that means Europe, the Middle East, and Africa. So this is like the version of the firmware that they ship with products in those regions. I don't think it makes much of a difference, particularly because we're only looking at this firmware, which is the latest version of the firmware, in order to get a very general idea of what kind of software the router leverages. It's almost a certainty that whatever firmware version got shipped with the device is not the latest one, just given how old this product is. But anyway. So the first thing that I'm going to do is I'm going to download this tool called binwalk, which is an awesome tool. Pending kernel upgrade. Oh, I don't care. Which is a really awesome tool for just scanning through binaries that contain multiple chunks. It's going to look for key patterns of bits to figure out, okay, this chunk is compressed data, this is part of a file system, that kind of thing. Super useful when working with firmware. So if I run binwalk here on our firmware image, it's picked out some header at the first byte there. It gives us a firmware version which appears to be incorrect. That's kind of weird. And then another header of some kind, some compressed data with the original file name Piggy. I don't know what that means. And then down here at the bottom we see that there's a SquashFS file system. So SquashFS is a way of taking an entire file hierarchy, like the root directory of Linux, hint hint, and squashing it down into a single continuous chunk of data. So one of the other things that binwalk can do, what we're going to really leverage it for here, is to extract this firmware, which means pick it apart, separate it into its logical chunks, and allow us to work with it file by file. So I'm going to run binwalk again with this -E flag for extract, and I'm going to add a couple more. So the first one is R, which just means remove all of the files, all of the full chunks of files like the SquashFS file after they've been successfully extracted. It just helps keep the workspace cleaner. I'm also going to add this -1 option, which means if you come across a symbolic link, don't change it. Keep it intact. I don't care about whatever relevant security risks. Don't change my symbolic links. Just a personal preference for me there. And so when I do this, you'll see that we get a couple of errors. It says here, or warnings rather, it says that the extractor failed to run external extractor Sasquatch. Oh yeah. Okay, so since this version of SquashFS is pretty old, it can't be extracted correctly by the version of like SquashFS that I have installed in Kali. So I have to use this nifty GitHub repo where they actually patch your SquashFS install. So I'm just going to clone this down. It would help if I had Git. Really hope that warning doesn't keep popping up on us. But if it does, whatever. Okay. So I believe that, yeah, installing this is as simple as running build. So it looks like it downloaded the source for SquashFS and is now patching it and building it. And it gave us an error. Oh shoot. Collect 2, error, LD returned 1, exit status. Oh, okay. I've seen this before. So this can typically be sidestepped by just adding the C flag F common. So I'll just say C flags equals F common and then run build again. We encountered this one before. And it's just going to do that process over, except hopefully it will build correctly. And it looked like it did, so if I just run which Sasquatch, yes, okay, so we have it now. Great, so now I can go up here and delete the extraction folder that had all those errors in it, and I can just run that binwalk command again. And now it looked like it worked without giving us any warnings. So let's go in here and check out what we've got. So we have this file called piggy. Let's see what that is. All right, just data. I don't know. I don't really think that it's worth looking into that right now. So let's go into our SquashFS root. So this is the root of the file system that is included in this firmware. And as you can see, it contains all of the directories that you would expect on a Linux file system. Let's just look really quickly at how many entities are in here total. 539. Okay, so that's something that we can probably look at quickly by eye. So first thing that I'm going to do is just go down the roster here and try to look for any interesting files, just anything that stands out, and I'll make notes of them. In fact, I should probably make some notes here anyway. A little notes file. Call me weird, but I like taking notes in Markdown. So this is our recon section. I'm just looking for interesting files. Just anything that we think would be worth making note of. So first of all, in the bin folder, we see that we only have 2 binaries. So there's BusyBox, which is all of the Linux commands that you know and love included in one binary. And then you would just symbolic link things like cat to it so that you don't have to have all of these as like standalone binaries, just save space. And the other one here is EAPD. I don't know what that is. And at this point, I don't see much of a reason to care. So, continuing along, dev ought to be empty. Yep. What about Etsy? So Etsy has a few things in it. It's got a cron D link to a temp folder. Okay. So hint, hint, cron's probably involved. Let's make note of that. And that links where to temp cron D. That could be important later. We have a hosts file, typically not that interesting. Whatever this is, I'm not quite sure. There's a OpenSSL configuration file. Okay, so that's good to know. Now we know that HTTPS is probably supported in some way, shape, or form. And then we have protocols and services. That's pretty standard. You expect that on a router, and then another link. So not too much that's interesting there. What about lib? All of these look pretty generic. Micro C, libc, libmsl. I don't know what that is. Whatever. What about within this module subfolder? Ooh. Oh, okay, so this is just kernel stuff. Yeah. Okay, so probably stuff that's involved with interfacing directly with the hardware. Not terribly interesting to us at this stage. So next, mount. That should be empty. Yep. Proc should also be empty. What about sbin? So sbin's got a lot of stuff in it, but only one binary, and it's this RC binary. What does RC stand for? I always forget. The RC at the end of a file is related to the phrase run commands. Its use derives from the etc.rc files used in most Unix systems. Okay, so run commands. So that makes some sense, because a lot of these links in here are linking to RC. A few to BusyBox, but most of them to RC, including this init link to RC. So sbin init is typically what runs when the operating system first boots up. So that's good. So now we know that if we ever want to enumerate the startup scripts or the startup processes, just figure out, like, when this operating system first boots up, what processes get spawned. It's sort of like the equivalent of running PS when you have an active shell. We would want to pop open this RC binary in our reverse engineering tool of choice and kind of root through the code, trace out the logic to figure out, okay, well, what services get spawned on startup. That, depending on the situation, that might be something that you would do right away. It might not. Let's leave it for now, but certainly make note that it's there. Okay, so what else have we got here? We've got a couple of temp directories. Those are almost always empty. And yes, they appear to be. Unix System Resources always has some good stuff in it. Let's look in bin. So it looks like we just have more shell command type things, including kill all, root, sort, and wget. Okay, so that's interesting. So maybe somewhere down the line, if we're able to execute our own commands, it might be useful to be able to download stuff onto the router's file system. So that'd be a good thing to make note of. Here we have usr bin wget. That's there for our use, and it's the BusyBox version. Okay, what about the lib folder? Okay, a lot of libraries that I don't recognize right away. libcrypto, more cryptography stuff. Network configuration. Non-volatile RAM, okay. It's kind of interesting. SSL, whatever libzebra is. So none of these really stand out, but what about in those subfolders. Okay. So IP table stuff just seems more system-y than I really want to work with right now. I don't know. I never really find that looking at libraries up front is terribly useful unless you see something that really stands out. So let's stop there. What about in local? Uh-oh, more SSL. Alright, so it looks like there's only the one file, given that tab completion just led me right there, and it's another OpenSSL config file. I'm not going to bother to look in there. It's all pretty typical, non-interesting stuff. What about an SBIN? Ah, okay, so here we see a whole bunch of binaries. And these are standalone. We notice we have cron, we have DNS mask, we have HTTPD, so that's going to be our web server, almost always. That's kind of a sure bet. We have an NVRAM binary, we have OpenSSL for generating certificates, that kind of thing. TFTPD, I forget what that is, but that's a daemon of some sort. We have dynamic host configuration, alright. And we have a designated binary for UPnP. So UPnP stands for Universal Plug and Play. That's good to know is going to be present on there. If you don't know what Universal Plug and Play is, it's basically this extension to HTTPD. It's just a product specification used by, or protocol specification rather, for IoT devices and routers to discover each other on the network, advertise different services, get spun up easily, and it's typically unauthenticated. So that in and of itself would be a viable attack vector. Let's make note of some of these other things. So we know we have cron. That might be useful somewhere down the line, particularly if we get to the post-exploitation step. We have DNS mask. That's probably going to be listening on a port. Let's see what else. We have HTTPD. Good to know where that is. That's our web server. That's definitely going to have an open port. And of course we have UPnP. I wonder what Zebra is, but probably not worth looking into right now. Okay. So what else is in Linux system resources? Oh, just a link to the temp directory. Okay. So last but not least, there's this www folder. So this, as we might expect, is going to be our web client. And it looks like it just has a bunch of pages corresponding to the various pages on the management console. And interestingly, they're .asp, which is active server pages. So that includes stuff like scripts, and in addition to HTML, it's, I guess, like an alternative to the normal HTML and JavaScript framework for like making a front end. It looks like it's including both, though. I'm not sure what to think about that. But in any case, you don't see ASP very much anymore. This is the kind of thing that was a lot more common, 10 or 15 years ago, which sort of makes sense. I believe that this router first hit the shelf in like 2009 or something like that. It's Obama era. So, okay. Probably not going to be that useful to root around in the client right now. So that's good. We have a relatively unsophisticated file hierarchy here. Not that many files, just I think we saw something like 540. So pretty manageable, pretty small footprint. So with those notes that we've already taken, I think it's probably appropriate to leave that there for the time being. Let's take a peek at the release notes. So release notes are useful because as firmware updates come out, they typically introduce new features, patch known vulnerabilities, and that sort of thing. So it can give you an idea of the life cycle of one of these routers. So we see that in the latest firmware version here, which is minor version 18, build number doesn't really matter. All they did was address a manufacturing issue that we don't need to care about. Previous version, went into compliance with something, okay. Resolved a cross-site scripting issue and code injection via DHCP. Okay, interesting. That's something to maybe make note of. You know, any time where you see that a major vulnerability in the product that you're trying to hack was patched in the latest firmware, that's good to make note of, because it could be the case that one of these vulnerabilities affects the version of the firmware on the router that shipped with our router, as opposed to the latest one. It's entirely possible that the version of the firmware that shipped with our router is not up to date. And even though ideally you would want to get a Vuln in the latest and greatest firmware, a Vuln in an old version is still a Vuln. Still fun for our purposes. So, okay, we're looking at release notes here. So in version 16 there was a vulnerability in the UPnP stack, but it doesn't tell us what it is. Still might be worth making note of for later. That was fixed in what? Minor version 16? Okay. There was another cross-site scripting issue. It's kind of generic in build 16.2. Yeah, why not? Can't hurt to make note of this stuff up front. And then there were a lot of changes in version 14, so they updated I think that's point-to-point tunneling protocol. Internet connection functionality, probably not a big deal. Issue with UPnP, issues with access control, not functioning in router mode. Oof, that's bad. Time zone stuff. Okay, ton of things fixed in 14. Might as well just copy this. Well, maybe not the whole thing. What about just the UPnP vulnerability? And that's probably enough. We can go back to this if it becomes necessary. Because once again, we still don't know which version of the firmware shipped with our router. It may well be the latest. We just don't know at this point, or we're pretending not to know. Okay, so I think I'll leave it there when it comes to the release notes. So something else that is always a good idea to do when you get a fresh product is to look for other existing vulnerabilities, stuff that may not be directly referenced in the release notes, particularly because these release notes came out with the latest version of the firmware, which was in 2016. So it's entirely possible that some researcher has subsequently found a vulnerability, after the period of time that it was actively supported, and wrote up a blog or reported it in some other way, and that could be very useful to us in gaining additional access to the device in service of finding our own vulnerabilities. And as a matter of fact, that was exactly the case in my exploration of this router. So I came across a vulnerability that was found in 2021, so just last year, long after the period of time that this product stopped being supported, from a researcher out of Israel who hacked a very, very similar router. So this differs from our model number by just one character. You just drop the L off the end. So it stands to reason that this is a very, very similar product. It could be a parallel product, it could be like the previous generation or whatever. But it's an entirely valid question to ask as to whether or not whatever vulnerability he found is also present on the router that we have here, even though it's a slightly different model. So we won't dive too deeply right now into the details of the vulnerability that he found. We'll just kind of cut straight to the chase, and so we can understand this at a cursory level. So here's the vulnerable chunk of code. Let's take a look at this for a second. So basically what he did is he figured out that there was a command injection vulnerability in this router and used it to download a reverse shell that he cross-compiled and used that to actually get like an interactive shell session going. So what's a command injection? A command injection is where there is some value, some user input that you control that finds itself getting format stringed or something similar into a call to the system function. So we see that right down here. System is a C function that just takes a string that represents a Linux command. In this case, it's a copy command, and then executes it on the underlying Linux operating system. So what he found is that this value here, this looks like it's decompiled C code from Ghidra. I believe that that's how they annotate variables. He discovered that this value here is user controlled. So what's happening is the value that winds up in this variable is getting read from non-volatile memory, specifically the value of UI language. So this, under normal circumstances, would have, like, for example, the value EN, if you want to, view your management console, say, in English. Or it'd be FR if you want to view it in French, SP for Spanish, DE for German, that kind of thing. But what he found is that when you set this UI language value, there's no validation that gets done on what value you set for UI language. Typically, this is done directly through the management console. Oh, I should have mentioned, he does in this blog, that this chunk of code is from the HTTPD binary. So the file that serves the management console. Just how you configure particular settings for your router and that kind of thing. So typically when you're setting the UI language, you would do that through the client. All the scripts and stuff that were in our www folder. But if you don't, if you decide to just use your own post request and use netcat or some similar tool to just send it over the wire to the router, it'll still process all of that information, all those settings that you update. And it performs no validation on what UI language is. So he does a two-part attack. So the first packet that he sends is just a post request which contains some malicious payload, and it gets stored in non-volatile memory as the value for UI language. And then he spoofs a firmware update in order to get this function to trigger. So then the malicious payload that corresponds to the UI language here gets loaded into memory and then dropped into this copy command here and executed by system. So what he figured out that you could do is replace this %s, the %s token here, with the following. So you put first a semicolon to terminate the command there, and then added his own command. So just for example, that could just be touching a temporary file that just says pwned, for example. It could be whatever you want. He actually used wget here, but just to keep matters simple, we'll stick with touch. And then put another semicolon in there. So in effect, your system is going to be executing 3 commands, but 2 of them are going to fail. This leading command is going to fail because, of course, copy requires 2 arguments, a source and a destination. And this last one is going to fail because that's not a valid command. That's just the trailing fragment of the copy command. Now this command in the middle, since it's surrounded by semicolons on both sides, is going to execute no problem, provided that it's a valid shell command. So this is a classic OS command injection. And he figured out how to trigger that on this similar router to the one that we're working with. So that got me thinking, well, is it possible that the same HTTPD binary is being reused in this later product? Or, at any rate, is this vulnerable chunk of code still present? So to verify that, we can just grep for this string here. So I could just run strings on the HTTPD binary, which I believe is in USR sbin. Yeah. So I'll just run strings on that file, and I'm sure that there are a ton. So we'll just pipe that to grep and look for, let's just say copy www. That should be enough. And we see that there are 3 matches, one of which is this vulnerable format string. Great. And then the other 2 happen to also be visible in this snippet of code. So this is really encouraging. This means that in all likelihood, unless there are some other changes that made this path unreachable, this exact same vulnerability that is described at great length and detail in this blog also affects the router that we have here. Now, I didn't see this documented anywhere. I went into, I actually did some digging on this vulnerability. I figured out the CVE number because our researcher friend here did report it. But the MVD entry is kind of cryptic. It doesn't mention either of the routers here, neither the one that we have nor the one in the blog, but instead this older version of router from likely the same series. I'm not quite sure why, but you can tell it's the same vuln. It references that UI language parameter, the vulnerable function, HTTPD, everything. It also says, note, this vulnerability only affects products that are no longer supported by the maintainer. Okay, so this is all very, very promising. These are things that we can likely leverage down the line if we want to get a cheap reverse shell on our router. Now, in and of itself, this isn't terribly valuable. We don't just want to prove that a vuln exists on this new product. We want to find our own. But it'll give us access to an interactive session on the device. We can run commands. We can do a lot more detailed recon, get a lot more information about the running processes of this router. So at this point, I'm going to shift to actually working with the router itself. So I took the liberty of getting this set up with all the defaults ahead of time. So I'll just go ahead and connect to it right here. I'll hop off our lab network here in Hillsboro. Connect to our router. And so the first thing that we want to do now that we're actually interacting with the router directly is to try and narrow down our attack surface. So since this is a router, any conceivable attack that we have is probably going to occur over the network. I think it stands to reason. So the first thing that I'm going to do is use Nmap, which requires no introduction, to do a port scan, see what open ports are available on this router. I'm also going to use this -A flag, which basically means run a bunch of scripts that tries to identify what services are sitting behind those open ports. And I know that the IP of the router is pretty standard, so let's get this port scan running. Oh, I need to install Nmap. That would help. Ah, rats. Of course, that router is not connected to the internet. Oops. Now we can install Nmap. Pending kernel upgrade. I don't know what that means. I don't really want to look into it now. Seems like everything's running, so we're just going to ignore it. So now I can connect back to the router and run our service discovery command. This is definitely something to make note of. Taking that sweet time Nmap is. Okay, great. So now it's returned a whole bunch of results. I'll just copy this off here. We can kind of pick through it. So first things first, we see that port 80 is open. All right, great. That's our web server. That's just normal unencrypted HTTP traffic that gives us that management console. And of course, it's going to be password protected, so we aren't allowed to pull down any information other than the fact that we're not authorized. We also notice that port 443, which is HTTPS, is also open. No surprises there. We knew that SSL was already present on the device. And then there's some certificate information that I don't think is worth looking into right now. And then we have this higher port, which is 5431, which Nmap is telling us is UPnP. Now, you can't always trust Nmap's guess as to what the service is going to be, but in this case, I think it's a pretty safe bet, particularly given that we already kind of established that UPnP is supported, as there's a designated binary for it. So none of this is too surprising. So basically, we have two services here. We have our normal web server, and we have UPnP. So those are our two possible attack vectors. These are our network-based attacks that we could launch over the network. They're either going to affect UPnP or HTTPD. So it's sort of dealer's choice as to which one we go with. I'm going to run with the web server first and look into this further, but we could totally go after UPnP too. That's a totally viable attack vector. We're just going to stick with HTTP. So given that we're going to do that, the next question is, well, how do I supply my own input to that HTTPD binary that's running the web server? Because it's great to know what port it's listening on, but if I actually want to supply data that's going to be processed by that binary, by that running program, I need to know what format it's expecting data to be in, other than just to know that it's going to be coming in over HTTP. So to do that, I'm going to start a Wireshark capture here, and I'm going to open up the management console here in my browser. So that should be available just by going to the router's IP at port 80, and immediately it prompts me for username and password. I set this to just admins to keep things easy. Let's not save that for now. Okay, and so we're presented with this landing page where you can do various things like, set static IPs, use different configuration protocols for assigning IPs. We'll just keep the default for that now. And we can go to, any number of these various tabs and look at all of the different places where you could possibly supply user input. But I don't think that there's any real need to do that here. We should notice, though, that up in the top right, we are given the firmware version. So this is the current firmware version on the device. It's minor version 14. So we're definitely going to make note of that. That is good to know for sure. Maybe cross-reference that with some of the release notes later if necessary. But I still want to know if I make some change via the management console, how is that change going to be transferred from the client to the server so that the server can update its internal configuration and that kind of thing. So I think that what we'll do here is just make a really small change, and that can be as simple as just turning off HTTPS. let's just say no, I want all of the traffic to be unencrypted, no matter what. So I'm just going to save settings there. Looks like we're going to get redirected in a few seconds. Thank you. And now that box is no longer checked. So now I'm going to go back over here and I'm going to stop this packet capture. Maybe make this full screen to make it a little bit easy. And now I'm looking for a post request or patch or whatever was initiated when I hit save settings there and made that change. So there were a lot of packets here, some DNS stuff, and there's our HTTP. Simple service discovery. Okay, so that's probably UPnP related. That's worth making note of. Ah, here we go. Here's our post request. So if I follow this TCP stream, I'm going to get the entire dialog associated with this update here. And I don't really care about the response. That's just going to be an HTML page with, by the looks of it, a bunch of JavaScript in it. Yeah, this is all HTML, JavaScript, okay. What I really care about is this post request. So how did the client send the data that initiated that update to the settings, the turning off of HTTPS? That's what I care about here. So I can just minimize these for now. Let's take a look at what that post request looks like. And it looks like we're making a simple post request to the apply.cgi endpoint with a bunch of headers that I don't really care about. Actually, it might be more useful to view this in the little markdown previewer over here. That way it's all, the request body is going to wrap. Okay. So none of this is terribly interesting. So it looks like in the request body we have a whole bunch of key value pairs that are separated by ampersand, so sort of in URL parameter format. And I'm looking for something that involves HTTPS. So get remote management HTTPS is 0. Okay. HTTP enable is 1. HTTPS enable equals 0. Okay, so previously we saw from the Nmap scan that it was definitely open. HTTPS was enabled. Now the client is telling the server to set the HTTPS enable status to 0. In other words, turning it off. Okay, so it stands to reason from here that most, if not all, updates to configurations are sent from the client to the server as these key value pairs in a post request body. Okay, so that's good to know. In fact, it's crucial to know. So the next question that you might ask is, well, now I know how to send my own data, my own information to the router, but how does it get processed once it gets there? So in order to do that, we're going to pop open the HTTPD binary that we extracted from the latest version of the firmware. Now keep in mind, this is the latest version of the firmware, not the version of the firmware that's running on the router, but we're counting on it kind of being close enough at this point. In my favorite reverse engineering tool, which is Binary Ninja. So we'll just make that full screen. And I'm going to search for this submit button parameter. Let's just see where this parameter gets parsed. So I'll search through the strings for submit button. We can see down here that it occurs in two different places. Let's just go to the first one. So it's in this function Godzilla CGI, okay, and it looks like it appears as a hard-coded string literal passed as an argument to the getCGI function. So let's take a peek at getCGI. So it looks like the argument to getCGI just gets passed straight to this hsearch _r function. So you see programmers out there will know that hsearch is how you query a hash table. And that first argument is the key. So now we know that the arg number 1 is going to be a string and it's the key. And this fourth value, I believe it is where you store the result, or where hsearch stores the result. If we kind of trace through the logic here, it looks like that is in fact what gets returned. So you can just rename this to value. It's the value corresponding to the key that gets returned. Okay. So this kind of makes sense. If you think about this as a key value pair, submit button has a corresponding value. In this case, I believe it was management. Yeah. Then all this is doing is just querying a hash table that presumably contains all of the different key value pairs that are included in the request body, and returns only the value that we care about for further processing. As we can see, this gets used later on. It's validated for cross-site scripting and used in various ways. Okay, great. So now we know how data gets sent from the client to the server, and we know how it's parsed on the other end. So we're already well on our way to figuring out how to inject our own stuff in here. Fantastic. So I can just save that off, or actually, you know what? I'll just go ahead and keep it open. We might want to use that later. So there's a lot more that we could do at this stage, just more playing around on the management console. But what I would really like to do is get some more detail. I kind of want to follow up on that vulnerability that we found, or not found, but that we learned about in this blog, and see if we can actually get a shell on the router. So I remember that this guy included a POC here. Yeah, he made a repository for it. So let's take a peek at this. It's a GitHub repo. Oh, yeah, that requires internet, doesn't it? I haven't connected the router to the internet, just FYI. Okay, so now we should be able to load this up. Alright, so this looks like instructions, and all of this is Python. Okay, great. Well, I'll go ahead and clone this. And it looks like, well, you know what, it's always a good idea just to follow the instructions. So just for good measure, I'll go ahead and install whatever requirements are needed. Okay, looks like we already have all of them, that's good. And you know what, maybe I'll just create a script for this. I'll just call it run exploit. Run that with bash. Let's copy all of this stuff in there. When in doubt, follow the instructions. So it looks like the router host has a different IP. So I'll just change this really quick. That's our IP. Username and password are the same, interestingly enough. Ooh, what's my IP? Let's switch back to the router. Just run IP today. Okay. Uh-oh. It doesn't seem to appear here. That's the wrong subnet. Okay, that's probably just because I'm using WSL. So if I just roll through here, maybe it'll tell me where the addresses start. Oh, here we go. Okay, so starting IP address is our subnet starting at 100. Okay, so I bet that my IP on this network that includes only my host and the router is 192.168.1.100. A little bit of guesswork here, but I think it's probably a safe bet, all things considered. So I'll just keep that the way it is, just change the subnet part. There we go. And then there's this attacker HTTP service host. Okay. Oh, that's right, because we have to set up a server to serve up the reverse shell that he downloads. Yeah, okay. So that's this bit. And then we need to start a netcat handler to receive the reverse shell. Okay, and then it's running the exploit. So given that I'm working in WSL, I'm just going to have to comment all this out and do that in PowerShell. Fortunately, I know how to do that, so I'm just going to change directory into here. This is where we'll set up our Python server. And I have to copy the reverse shell. So there's this rev shell folder that contains two things. So let's see. This should be source and the binary. Okay, great. Cool. So this is an L file. This is the cross-compiled reverse shell for MIPS little endian, and then here's the source. So let's just take a look at the source for good measure. So this is a super simple program, as you can see. Literally all that it does is create a connection, and then on that connection say, okay, well, yeah, we're interacting with bin sh. Great. And so this is already cross-compiled, so we need to copy it into my Windows system where it is reachable from the outside world. Oh, looks like I've already done this. Makes sense. Okay. So there we go. Now we'll go back to PowerShell and we'll start up a Python server. This, by the way, is the Python 2 syntax for doing this. I'm using Python 3, so it's just going to be a little bit different, but it's the same exact thing. And then we're setting the server port to 8000. Okay, great. So I'll just go ahead and start that server right there. Now I'm going to need another one that is going to be our netcat handler. So it's netcat.exe. Is that right? Yeah. Yeah. And then we're going to say that we're listening, and we're going to listen on port 4141. Pretty arbitrary, but just keeping the defaults here. Okay, so now this is just listening for connections. It's not really doing anything now. And then this final command actually runs the exploit. Now, do I have just normal Python? I do. Okay, good. So I don't need to change that to Python 3. All right, well, moment of truth. Let's just make this runnable and see what we get here. So here we go. It says it's running this command that is attempting to download the reverse shell. Let's see if it did. Okay, yep, it worked. So we got a GET request for the reverse shell. And then it's making it executable. And then it's running the reverse shell on our IP on port 441. So now, if I were to example just run ls, assuming that I got the IP correct, this should give us some results. And it does. Okay. So these are all those ASP files that we saw in the www folder. So it looks like the HTTPD program is being run from that folder, maybe? Not quite sure, I guess it doesn't really matter. But if we ls in root, we see the file system that we would expect. Okay, fantastic. So now we have an active session on the device where we can issue commands and read more information. So it's time to do just a little bit more recon here. So what happens if I run ps? So if I run ps, I get all of the processes that are currently running on the device, including, by the way, the command that is spawning our reverse shell, or that spawned our reverse shell. And as you can see, it's all janky since it was done by command injection. So let's just copy this off. And let's see, what else can we run? We can run df. No, df isn't there. Okay, what about ifconfig? I saw that. Maybe... Oh, there we go. Okay, so we have a bunch. I don't know if I want to copy off all of this, but we definitely could. Certainly the first couple. Or just all of it, why not? It can't hurt. Yeah, that's a lot. But it's always good to copy off this information before you've done any experimentation on the router, just because, you know, things might change later on. So what else? What about mount? Not found. Okay. I'm just trying to think of commands here that are going to give us interesting information about the status of the system. Okay. Well, I'm just going to put that kind of down below. Good to keep if necessary, but I don't want it getting in our way here. So what else can we do here? Well, not a lot other than just create some files. Let's see if the whole thing is writable. So let's just try to touch the file in the root. Okay, read-only file system. Alright, well what about var? Alright, cool. It looks like I can write to var. I can almost certainly write to temp. Yep, there we go. And we see our reverse shell, which got renamed to X right there. Okay, great. Now one thing that I can't do, or, well, maybe I can, but I'm not sure what command would do this, that I have access to. I can't see how much space we have, but I can, of course, as we've already demonstrated here, use wget to download stuff from my host to the router. So that's really useful. Tremendously useful, actually. So at this point, we've been able to do recon at 3 different levels. We first took a look at what information we could find without ever even having to touch the router, without even having to get it set up. We were able to download the latest firmware, figure out roughly what kinds of files, programs, services are on there, and we were able to find a vulnerability that does in fact affect our router, and then eventually confirm it. Once we were able to get the router up and running and load up the management console, we were able to figure out which ports are open. We noticed that there was the web server and a UPnP service, which I believe we also confirmed here just by the PS output. Yeah, there it is. UPnP is definitely running. We were also able to figure out how user input is transferred from the client to the server and how it gets parsed on the other end. It gets put into a hash table, and that get CGI function fetches it. So then once we were able to get this POC working, this command injection exploit, we were able to get a full reverse shell with, I believe, root privileges. I'm pretty sure that this is running as root. Yep, UID 0. Okay, so HTTPD is running as root. We were able to get a reverse shell on the router. So that's fantastic. We've been able to do recon at 3 different levels, and we have the ability to run arbitrary commands on the file system, provided that they're supported. So we're now set up really well to look for vulnerabilities and develop our own exploits. But that's for another video.